Hi, I'm Beth Faber from the Hydrologic Engineering Center, and this is part 2 of the lecture on analyzing hydrologic time series. This is the 4th lecture in the class on statistical methods in hydrology. So here we are in our list of topics. We're still on annual extremes, but we're looking at longer durations of average flow or longer duration volumes. Why are we interested in looking at longer durations? Well, if we're looking just at a channel, then it's the maximum flow that gets out of the channel and can cause damage. But if we're evaluating reservoirs that store floodwater, then we're more interested in the volume of water across a certain period of time, right, than just what the maximum flow was, because we need to evaluate the likelihood of a volume greater than the reservoir can manage. So we're looking at something called volume frequency analysis. Although it's called volume frequency analysis, we actually do the analysis on average flows. So the average flow is just the volume of water divided by the amount of time it took to accumulate that volume. So they're really the same thing, and we'll see why average flows are a little bit easier to work with. Right, so we're going to be creating a family of frequency curves, each with a different duration. And to start, we're going to be extracting annual maximums for the various durations from our period of record time series, right? We have duration X, that might be 1 day, 5 day, 30-day durations, and those maximums are going to be based on an X day moving average. So for the 5 day, we'll do a 5-day moving average across our entire period of record, and then we'll go through and extract the maximum 5-day average from each year, right, to build a data set of the maximum 5-day averages. We'll have a data set like that for each duration, and then we'll just do a frequency analysis on each duration. If it's unregulated flows, then perhaps we'll just do a Bulletin 17B and C type procedure. Right, so here's what the longer duration averages look like. This is a snowmelt watershed. This is the Kootenai River in Montana, flows north into Canada and back down into the United States, eventually into the Columbia River. And we're looking at, because it's snowmelt and it takes a little bit longer, we're looking at longer durations. We have 1 day, 15-day, 30-day in green, 60 in black, 90-day in pink. And as you can see, when we average over longer periods of time, we're including lower flows. And so each time the duration gets longer, the average gets lower, right? Now we're going to go through the period and pull off each of these maximums from each year. Here's what it looks like for a shorter duration event that's only a couple of days, and also getting a look at those moving averages. So here on the left, we have a single year with an event. The blue is a 1-day moving average, green is 5-day, red is the 10-day moving average, and we go in for each and pull off the peak value. Having done this for each year, we create a data set that spans the entire period of record. We actually create 3 data sets. So the blue is the 1-day maximums, and the green dots are the 5-day maximums, and the red dots are the 10-day maximums. Each of those is a separate data set, and we'll get a separate frequency analysis. Using the SSP software that you'll be introduced to tomorrow, we get a table of the maximum flows for the maximum average flows for each duration. So we have our water years on the vertical, and then we have our durations across the top. And for each water year, we see the maximum flow of that duration and the date that it occurred. So 1956 water year is one of the large flood events of the record that happened in December 1955. And if you look to the 1-day, 3-day, 7-day, you can see the average values going down as the duration gets a bit longer. This is what our data is going to look like as we plot each data set versus plotting positions, and then also fit log Pearson type 3 distributions to them, right? So we've got, with annual maximums, we have the shortest duration is always the most extreme. So the 1-day duration is going to be the highest. And as we discussed, the longer duration flows get lower and lower. We can also see why we're using average flows instead of volumes, because the volumes at the longer durations would be getting longer and longer, and so would be plotting higher and higher on the axis. We wouldn't be able to plot all of these different durations together on the same axis. With average flows, they plot a lot closer together, right? So we can see what we're doing just a bit better, right? So what we have created here is a family of frequency curves for the same site that need to be consistent with each other. We'll talk a little bit more in a few minutes about how to ensure that they're consistent. All right. Another important question, though, is how we define a year when we're pulling out the maximum value of each year. So another plot that we can create from the SSP software is this one that plots the hydrograph of each year on top of each other, and it gives us a view of the hydrology for the location. So as we can see, this site in Northern California, we have a dry period in the summer, and then in the winter period from November into the following April or so, we might have rain floods. And if we're going to be looking at longer duration averages of high flow, we want to be very careful that we don't break the flood season. So this period of November through April has to stay whole in each of our years, right? We wouldn't want to break January 1st and maybe break the highest average 30-day flow for the year. So in this case, for high flows, we're going to break maybe September 1st or the normal October 1st water year. Right. Now for low flows, if we're pulling out our annual minimums, then we're going to want a different break of the year. If we're doing low flows, we're interested in this summer season of low flow. And so we'll go back to breaking the year maybe at January 1st again. So we've created this family of volume frequency curves for the purpose of creating synthetic events, right? So we wanted to create events that have a given exceedance probability that we can route through our models. Right, the first step was to perform the volume frequency analysis and get this family of frequency curves for various different durations. Next step is to choose an historical event to be our hydrograph shape, and then we're going to scale that historical hydrograph to match the average flows or volumes of a chosen exceedance probability. Okay, so if this is our family of frequency curves and we want to make a 0.5% exceedance or 200-year event, we're going to pull off these 200-year values from each of these frequency curves to get flows. Okay? Now, we could choose to scale a hydrograph such that it matched the average flow for all of these durations and create a balanced hydrograph. I'm going to show choosing just one of these durations, which is relevant for the reservoir at the site. I'm going to scale to just the 3-day duration in this case. Right, so here is an historical flood event from this location. It happened in 1997. Okay, American River at Folsom. Folsom is that reservoir that I mentioned on the American River. So I'm showing here the 1997 event and then also the average 1-day, 3-day, 7-day, and 15-day duration and what their estimated exceedance probabilities are. And as I said, I'm going to choose only the 3-day. So I'm going to scale this hydrograph such that the 3-day average flow goes up to match the 0.5% or 200-year average flow value. As you can see, it brought the entire hydrograph up. So here's what the simulation of the actual 1997 event looks like in our reservoir simulation model. And as you can see, the flow the release did not exceed the channel capacity because the storage level was fairly comfortably within the reservoir storage volume. But if we route instead the scaled up version of this event, we fill a lot more of the flood storage and the release gets up to the next flow threshold. Okay. What that's going to look like on the graphical frequency curve that we were interested in extending, if you remember from the previous part of this lecture from part 1, in that we had the historical record plotted as these blue diamonds and were unable to extrapolate beyond the channel capacity. Now we are able to plot a 200-year value and also did a 500-year value at releases that are over this original channel capacity or original objective flow. And then we can estimate a curve with these new values that approaches the unregulated frequency curve. Now, if you have other historical events that are differently shaped, you might scale some other historical events in the same way. So this is a flood event from 1986 from that watershed. The 3-day volume was actually quite similar, but it's a differently shaped event that has two peaks. The peak in each individual peak value is a bit lower, but it provides a very different challenge to the reservoir. So when I simulate these events, the 200-year and then also a 500-year event through the reservoir, I get these higher flows for each of those exceedance probabilities. Now, remember, the assumption that we're making is that the exceedance probability of these releases is equal to the exceedance probability of the inflow. Again, perhaps that isn't always true, but that's the assumption we're making for this analysis. So now I have, for each of these two exceedance probabilities, I have two flows. So maybe my final frequency curve can be this higher curve that takes into account the different possible shapes of the hydrograph in the watershed. So let's back up for a moment to the family of volume frequency curves or average flow frequency curves. I had mentioned there was perhaps an extra step to make sure that the family of frequency curves is consistent. We need to make sure that the curves don't cross. So we might need to smooth the parameters of the log Pearson type 3 distributions that we fit. Here's some volume frequency curves from a different location. We've got a peak frequency curve from instantaneous peaks, and then we've got 1 day, 3 day, 7 day, 15 day, and 30. Most of them are fine, but if you look at the 1 day frequency curve in red, it at the low end actually crosses the 3-day curve, and at the high end you can see that if we extend it a little bit further to the right, they would cross. And what's happened here is that the 1-day curve has a more negative skew coefficient than either the peak or the 3-day, and that's what gives it more of a downward curvature at the top and at the bottom. And so we're probably going to have to adjust the skew coefficient for the 1-day curve to make these consistent. Right? So we're going to look at the mean, standard deviation, and skew of the log flows and smooth them so that they make sense as a set. So here I've got each of the sets of means, the standard deviations, and the skews each plotted across duration. Sometimes we plot them against each other, plot mean versus standard deviation versus skew. In this case, I've plotted them all against duration. So first, looking at the means down here at the bottom, these actually look fine. So the mean is decreasing as the duration increases, and that was what we saw when we average over a longer duration of time. The flows get lower. For standard deviation, we have this 1-day flow having a higher standard deviation than the others, and we're just going to bring that value down. So the original values were the blue diamonds, and I'm going to have this hollow red diamond as my replacement value, and it fits in with the others. What we were expecting with the skew coefficient was that 3-day skew coefficient is quite negative, and we're going to move it up to be between the 1-day and 7-day. Nope, the 1-day and 3-day. And then over here, we've got the 7-day value. We're actually going to move down a little bit just to make it more convenient, more consistent in the set as well. So going back to the frequency curve, if this was my original family of frequency curves, now I've got a more consistent set. Right, so I'm going to go back up to the original and down to my adjusted frequency curves, right? So these make a better family of frequency curves that won't give us anything that does not make sense at the extreme exceedance probabilities. Right. Now, I had mentioned that it was possible to, instead of just scaling our historical event to one duration, I could scale to all of the durations if I chose. And this image is just a bit of a caution. Often that works very well, but sometimes it can change the character of the historical flood event. And so this is an example of the flood event that has a pretty wide peak. And when I scale to the peak and the 1-day and the 3-day and 7-day for a given exceedance probability, it has quite a different shape. It's not incorrect, and sometimes it doesn't even change the event this much, but it is something to consider. So far we've only looked at annual maximums at high flows. We're also interested in doing low flow frequency analysis and looking at annual minimums. So a difference between the two is we find that high flows that are unregulated often let us do a parametric model or an analytical probability distribution fit, like the log Pearson type 3 or others. We don't do a distribution fit for regulated flows. Again, as we saw in the first part of this lecture, those would need to be graphical, but unregulated high flows generally will fit an analytical distribution. Low flows, on the other hand, very rarely fit an analytical distribution, and we will more often go with a graphical curve for those. So let's look a little bit at low flow frequency analysis, okay, based on our annual minimums. In this case, with the annual minimums, we're looking at non-exceedance probability. We're interested in the probability of being less than the particular low values. And a common metric that we use for analysis for restoration or for low flow regulation is what's called the 7-day, 10-year low flow, right? So this is just one value off the family of frequency curves that we're interested in. The 7-day refers to the duration that we're averaging over, and the 10-year is the return period, which means the 10% non-exceedance probability, right? So the 7-day, 10-year low flow means that there's a 10% chance that the 7-day consecutive low flow is going to be less than this value in any year. Right, a caution is that with low flows, as the duration increases to months, actually this applies to high flows as well. As the duration increases, the amount of time between annual extremes decreases. So we are less and less likely to have independence between sample members, right, as we're looking at 3-month, 4-month, 5-month averages. Right, so 7-day is common. For snowmelt watersheds, a 30-day, 60-day, 90-day is common, but not much more than that. Right, so here is here's a family of low flow frequency curves for 4 different durations. In this case, we have the samples, the 4 different samples, plotted against their plotting positions, and we don't have any analytical distribution fits because it would not be a reasonable fit to the data. A reminder that we're looking at non-exceedance probability now, the probability of being less than our low values. Again, we have the shorter duration, the 1 day being the more extreme, which in this case is lower. Notice, though, that the values are a little bit closer together between the different durations. So with a peaky high flow, when you average across durations, you're going to get bigger differences between the 1-day flow and the 3-day flow. With low flows, they tend to be dipping much more gradually, and so the averages across the longer durations don't change as much. So the curves end up closer together. Right, so that metric we were interested in, the 7-day, 10-year low flow, the 7-day averages were in green. The 0.1 on the horizontal axis is the 10% non-exceedance probability, comes over to a flow of 510 CFS. Right. For minimum values, we're also interested in something like reservoir stages, right? So here is annual minimum pool stages on the reservoir on the American River. Folsom Reservoir. So this is the lowest value of each year. And I'm just going to make up some elevations here, but let's say we were interested in a boat ramp that's at 385 feet, and we want an idea of how often that boat ramp is going to be up out of the water. Well, in this case, it has a return period of 5 years, so about every 5 years, it might be out of the water, although we don't expect a 5-year interval. It's just on average every 5 years, but really a 20% chance of being out of the water in every year. And if they also had installed a much lower boat ramp at, say, 320 feet, then that one only has about a 2% chance each year of being out of the water. Right, so that's our annual minimums. Back to our topics. This next topic we're going to cover so briefly it's not going to get its own video. We're going to talk just a little bit about partial duration series or peaks over threshold, but you'll see this in a great deal more detail in the extreme value lecture on day 3 that Greg will put together. So because we're still looking at extremes, if we're careful, we can maintain the independence assumption. So Here is a different river. It's the Willamette River up in Salem, Oregon. These are unregulated flows. And the annual maximum series looks like this, these red dots that are the largest value in each year. But maybe we're interested in a threshold of about 80,000 CFS. And so we go in and pull all values that exceed 80,000 CFS. Now, these values were pulled carefully such that if we zoomed in on any of these years that has multiple peaks, we'll see that they are a certain time duration apart, and that flow does recede down to a base level before going up again, right, to be able to call them independent events. But as you can see, we have a whole lot more events than we did with annual maximums. There's many years that have several. Here's an image from our old guidance, just showing a quick difference between annual maximum and partial duration. So the annual maximum events are, again, the highest in each year, years 1, 2, and 3, regardless of how low a maximum might be. The partial duration series is all values that are over some threshold. So year 1 in this case has 2, and year 2 has nothing because the value doesn't exceed the selected threshold. Okay. The plotting positions for partial duration series have sometimes a different interpretation because plotting positions are intended to be an estimate of the exceedance probability, or for low flows, the non-exceedance probability. But if we have more events than we have years, then some of the rankings are going to be greater than n years. Right? And so if we have a rank greater than n, then we have a plotting position that's going to compute to a value greater than 1. That can't be interpreted as an exceedance probability. So instead, we interpret it as the average number of events per year. Right? Now, because it can't be interpreted as exceedance probability, we can't plot those events on a probability axis. If this axis was linear, then I would be showing all the partial duration events all the way down to 80,000. But because it is a probability axis, I'm only showing the events that are, let's see, I guess this was 75 years, so this is only the top 75 events. So what we have here is the partial duration series plotted in blue and the annual maximum series plotted in red. The upper end of the curve is usually very similar for annual maximum series, and that's because the largest events usually are the largest in whatever year they occurred. Sometimes we'll have additional events where we'll have a large event that wasn't pooled because it was the second largest in each year. But usually the top end is very similar. It's the lower end that makes a difference and shows us when a partial duration series analysis is more relevant. And it's when we're interested in the more frequent flows, perhaps below the median, because we can see here that the flows that have a much higher likelihood of occurring, we see that flows of this magnitude, about 140,000, and then all the way down to the 80,000, happen a lot more frequently than we would have expected if we only looked at the annual maximum series. So what I've showed here is an empirical or graphical analysis of the partial duration series versus the annual maximum series. We're going to have a much more detailed coverage of this topic with Greg on Wednesday within the extreme value lecture, and he'll cover doing an analytical analysis of the partial duration series. And that's going to be a little bit different because the analytical model for partial duration series has 2 parts. There's going to be one model for arrivals, or how often an event will exceed the threshold, and then a separate model for intensity, which means the magnitude of the event given that it exceeded the threshold. So that second one is a conditional distribution. Right, so both of these have to be fitted. The log Pearson type 3 that we use for annual maximum series usually isn't a good model for the intensity of events over the threshold. Normally we'll use something like a generalized Pareto more effectively for intensity, and we use a Poisson distribution often for arrival. Another reminder is that establishing the independence of the peaks is a lot more challenging when we're doing a partial duration series. We have to ensure that we are only pulling independent events that have a minimum duration from the previous event and also have had flow receding below some level. Right, so that was the end of the second video of this lecture, and next we're going to move on to daily flows and stages. So thank you, and I'll see you in the next video.